Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL January 2023 paper of Chemistry Unit 2. In the first question, we are given an apparatus to measure the enthalpy change of combustion. So we are given a spirit burner with methanol heating up a copper calorimeter containing 50 cm cube of water. We are told that after burning 0.2 grams of methanol, the temperature of the water increases by 16 degrees Celsius. For part A, we are given that the measurement uncertainty is 0.5 degrees Celsius for each reading. We have to find the percentage uncertainty when the temperature changes by 16 degrees Celsius. Here the percentage uncertainty will be the measurement uncertainty multiplied by 2. This 2 comes over here since we are measuring the temperature change. To measure the temperature change, I'll have to measure the initial temperature. So we'll have an uncertainty of 0.5 degrees Celsius there, and then I have to measure the final temperature. When I measure the final temperature, this uncertainty occurs again. So this happens twice. The measured value is 16 and multiply it with 100. We get a value of 6.25, so to 2SF it's 6.3%. Now in part B, we burn 0.3 grams of methanol, so instead of 0.2 we have 0.3, and before we had 50 cm cube of water, now we have 75 cm cube. Now we have to find the expected temperature change in this experiment. The shorter method would be checking the change in mass. So the previous mass was 0.2 grams, the new mass is 0.3 grams. This is the mass of the fuel. If the mass of the fuel becomes so now that mass of the fuel is 1.5 times what it was, and for water instead of 50 cm cube, now I have 75 cm cube. The volume also becomes 1.5 times what it was. Since the volume or mass of the object that we are heating and the fuel increases proportionally, the temperature rise must be the same as it was before, so 16 degrees Celsius. A more proper way or a longer way to do this would be finding the value of the energy change for 0.2 grams. So the energy for 0.2 gram was the mass of water 50 into C into 16. From here I find Q. The new value of Q will be 3 by 2Q, since the mass of the fuel is becoming 1.5 times what it was. The mass of heated liquid will be 75. The value of C will remain the same. I have to find the temperature over here. If I do that, the temperature change will come out to be 16. Now in part C, we are told that the students calculated enthalpy change of combustion is more exothermic than the data book value. If we look at option A, if heat was lost to the surroundings, our calculated value should be less exothermic. So if heat was lost to the surrounding, we will get a smaller temperature change, so we would have got a less exothermic value. Same case for incomplete combustion. If there was incomplete combustion, the temperature change would be smaller since less energy is released when the combustion is incomplete. This would give a less exothermic value for the enthalpy change of combustion. Also the same case over here. If methanol evaporated from the wick of the spirit burner, the temperature, in this case the mass of ethanol, so the mass of methanol used would appear to be more than it was. The methanol that evaporated was not combusted. This did not go through combustion, it just evaporated out. But when we are calculating the mass, this is also factored in. This will make the value come out to be less exothermic. Since it doesn't affect the temperature, but it affects the number of moles. So when we find Q equals to mc del theta or del T, it doesn't affect the temperature over here, but when we find del H, which is Q by N, where N is the number of moles, the evaporation affects the number of moles. So if methanol is evaporated, the number of moles that we calculate come out to be more than it should be. So the enthalpy will have a smaller magnitude than it should have. So it should be option D. If I use the molar mass of ethanol over here when calculating N is mass by mR. If I use the mR for ethanol, which is more than methanol's, I'll have a greater mR than I should have used. So the value of N that I get will be less than the actual one. If I get a value of N which is less than the actual one, I'll get a magnitude of del H which is more than the actual one. So option D will be our answer. The standard enthalpy change of atomization is defined as 1 mole or 1 mole of gaseous element being obtained from its standard form. So bromine standard form is Br2 liquid. Bromine is a liquid at room temperature. Bromine and mercury are the only two elements which are liquids at room temperature. So these two are out. And by definition, we know that standard enthalpy change of atomization results in 1 mole of gaseous element being formed. In this case, there are 2 moles. So option A will be the answer. Now on to question 3. We are given the bond enthalpy of the hydrogen-hydrogen bond, the chlorine-chlorine bond, and the HCl bond. From that, we have to find the enthalpy change of reaction of this reaction. Here, half a mole of H2 breaks. So the bonds broken will be 436 times 0.5. There is also half a mole of Cl2 being broken, so half or 242 into 0.5. And then we'll subtract the bond enthalpy for 1 mole of HCl bonds, which is 431. If we look at the options, this one corresponds to what we have found. Now in question 4, we are asked which compound has London forces as the only intermolecular force. HF will have hydrogen bonding between them. So 1 mole of HF will form a hydrogen bond with another HF. OF2 will have permanent dipole interactions, so will PF3. In these cases, the molecule is polar because they have a lone pair over here. Since there is a lone pair, the shapes aren't symmetric, and if that happens, the dipole moment doesn't cancel out. However, for CF4, there are no lone pairs. As there are no lone pairs on the carbon, if I draw the shape, the dipole moments will be cancelled out. So D will be our answer. Now moving on to question 5. we have to state which molecular has intermolecular hydrogen bonding. If we look at the structure of A, it is CH33N, so N with a CH3, another CH3, another CH3. The bonding of N directly is with carbon. The nitrogen doesn't have a bond directly with the hydrogen. They are bonded with the carbon is bonded to the hydrogen. For this to form hydrogen bonding, there needs to be an NH, an OH, or an FH. So a hydrogen with a nitrogen, oxygen, or fluorine. If I look in the second option and draw its structure, it basically is a carbon with a fluorine and 3 CH3 groups. In this case as well, we don't have a FH, OH, or NH bond. If I look at option C, we have COH, CH3, H3C, CH3. Here we do have an OH bond, so we can form hydrogen bond from here. And if I want to look at the last option, we have CH3, 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 COH. Also in this case, we don't have a NH, OH, or FH bond. In question 6, we have to show the hydrogen halides in order of decreasing boiling temperature. If I draw the graph of the boiling temperature of the halides, we'll get something like this. This over here is hydrogen fluoride, this is HCl, HBr, and HI. Hydrogen fluoride can form a hydrogen bonding, so it has a high boiling temperature. A lot of energy is needed to break the hydrogen bonding of HF. Now from HI to HCl to HI, in this pattern or this trend, as we go down the group after HF, the forces between the intermolecular forces between them are permanent dipole forces and London forces. The permanent dipole forces across HF, HBr, and HI are almost the same. However, if you think about the London forces, HI has the most electrons, followed by HBr and then HCl. The more the number of electrons, the stronger the London forces between them. So as we increase the number of electrons from HCl to HI, the London forces become stronger, causing the boiling temperature to increase again. So we'll have hydrogen fluoride, then we should have hydrogen iodide. Okay, so option A is out. After that, we should have hydrogen bromide and hydrogen chloride. B is our answer. Now in question 7, we have to find where vanadium has an oxidation number of +4. If I look at option A, if I consider the oxidation number of vanadium to be X, we get X plus minus 2 is equal to 2. So X is +4. A is our answer. If I look at the other options, this will be X plus 2 times minus 2 for 2 oxygen will be equal to +1. From here I'll get a value of X which will be +5. If I have VO3, I'll have X plus 3 times minus 2 is equal to -1. I'll have the value of X to be +5. In this case, VO4 3 minus, I'll have X plus 4 times minus 2. This is equal to -3. From here, the value of X will again be +5. So option A is our only answer. Now we have to find the formula of potassium manganate 6. Potassium manganate 6 represents that the manganese over here should have an oxidation number of plus 6. So if I want to find that, I have plus 1 for K and minus 8 for oxygen. So X plus 1 minus 8 is 0. So X is 7 or plus 7. This is not the answer. If I look in the following one, we have X plus 2 minus 8 is 0. We'll have X is equal to plus 6. B is our answer. If I explore the other options, I'll have X plus 3 minus 8 is equal to 0. From here we get X equals to plus 5. From the last one we get 2x, since we have Mn2, plus 6 minus 6 2s are 12, minus 12 is 0. We get X equals to 6 divided by 2, so we get a value of plus 3. So B is our answer, since it's the only option where the manganese has an oxidation number of 6. Now on to question 9. We are told that compound Q produces a red color in a flame test and a white precipitate when aqueous potassium sulfate is added to a solution. Since it produces a white precipitate, or it produces a precipitate when potassium sulfate is added, this cannot be a group 1 element, since all group 1 elements are soluble. So lithium is out of the question, so is sodium. Now if we look at the remaining options, barium has a green apple flame in a flame test. This will show a green apple color when its flame test is done. Strontium will have a reddish color. This is our answer. Now in question 10 we have to answer which of the following reaction produces more than one product. For the first reaction, the product is MgO. We have 2Mg plus O2 forming 2MgO. For the second reaction, CaCl2 is the only product. And for option D, barium hydroxide is the only product. Now when strontium reacts with water, it produces strontium hydroxide and water. This is basically a metal plus water reaction which will form this will be H2. So metal plus water will form a salt and H2 gas. Now in question 11 we have to find which equation shows a redox reaction that would not be expected to occur based on the trend in reactivity of the halogens. As we go down group 7, its reactivity decreases. So if we look at this equation, in option A, iodine cannot displace astatine, the other way around, the astatite cannot displace the iodine, since the iodine is more reactive than astatine. So this is out of our option. If we look at option B, chlorine is more reactive than the bromide. Since chlorine is more reactive, the bromide ions cannot displace the chlorine. This is not our answer. Between Cl2 and I minus, chlorine is more reactive, so the iodide ions cannot displace it. This is not our answer as well. If we come to option D, we have fluoride ions and astatine. Fluoride ions are more reactive than astatine, so the fluoride ions can displace the astatine. So this will be the answer. In this question, we have to find which reaction would have the greatest number of halide oxidized. Now, if I look at the first equations, the halides are F and Cl over here. The oxidation number on this is -1. Over here, the oxidation number of fluorine is still -1, so no oxidation happened here. If I look into B, the oxidation number of chlorine is -1 on the left and -1 on the right. No oxidation happened here as well. If I look in the third equation, we have bromine with an oxidation number of -1, and so it has KBr, where the bromide ions have an oxidation of -1. And on the right, we have bromine. In this, the oxidation number of bromine is 0. So bromine has been oxidized. If I look in the ratio of H2SO4 and bromine, 3 moles of H2SO4 has oxidized 2 bromide ions. So 2 by 3 bromide ions are 2 by 3 moles of bromide ions are oxidized by 1 mole of H2SO4. If I look at the last one, we have iodide ions over here with an oxidation number of -1, and we get iodine with an oxidation number of 4. Here, 8 moles of iodide ions are oxidized by 9 moles of H2SO4, so 8 by 9. If I look at their values, 2 by 3 is around 0.67, 8 by 9 is around 0.89. This is a larger value, so D is our answer. Now in question 13, we have silver nitrate in aqueous ethanol added to separate halogen-alkanes. We have to find which would form a silver halide precipitate in the shortest time. We have learned 2 different orders of the reaction rate of chloroalkanes, halogen alkanes with silver nitrate in aqueous ethanol. The options, 3 of the options have chlorine as the halogen, while option C has iodine. As we go down as we go down group 7, okay, we have 2 options with iodine. So this is iodine. This is Ci, not Cl. We have to be careful about that. So we have 2 options where iodine is the halogen and 2 options where chlorine is the halogen. Now, if we go down the halogen group, so from chlorine, bromine, iodine, so halogen, chloroalkanes, bromoalkanes, and iodoalkanes. As we go down, the rate of hydrolysis increases, so rate increases. So it shouldn't be chlorine, as Ri will have faster reactions. So this is out, this is out. Now we have also learnt about primary, secondary, and tertiary halogen alkanes. So primary, secondary, and tertiary. In this case as well, the rate increases as we go down. So a tertiary halogen alkane will have the fastest reaction. If you look over here, option C is a primary one, while option A is a tertiary one. So option A should be the answer. Now in question 14, we have this bromoalkane over here, which is heated in ethanolic potassium hydroxide. We know that if we heat a halogenoalkane in ethanolic KOH, we get an alkene. It undergoes a dehydration reaction and we get an alkene. If we remove this bromine in a dehydration reaction, the double bond may form over here or here. So we might be tempted to give 2 over here, but we have to keep in mind that geometric isomerism will occur over here. So if the double bond is on the left, we have hex 2 in, we have a 6 carbon chain with a double bond on the second carbon. C double bond, C H over here, CH2, CH2, CH3 over here, and an H over here. We can have a E isomer for this and a Z isomer for this. So 2 from here, and if the double bond is over here, we'll have hex 3 in a straight chain of 6 carbon with the double bond on the third carbon. H over here, H over here. We can have an E or a Z isomer here as well. So 2 more from here. So 2 plus 2, we get 4. We can get E or Z hex 2 in, or we can get E or Z hex 3 in. So E hex 2 in, Z hex 2 in, E hex 3 in, and Z hex 3 in. 4 of them. Now in question 15, we are given which compound is least likely to have a peak at M by Z 43 in its mass spectrum. The M by Z peak at 43 can be caused by CH3, CH2, CH2 plus. This is 15 plus 14 plus 14, which comes out to be 43. Or it could be due to CH3CO plus. So we have 14 plus 12 plus 16. This also adds up to 43. Now if I look at the first molecule, we have a CH3CO over here. So this is the structure of this compound. We have a CH3CO, CH2CH3. If the bond is broken over here, we get CH3CO, which has a peak at 43. So this is not it. In this case, we don't have a 3 carbon chain together. So this is the structure: CH3, CH2, NH, CH3. If I break the bond over here, I get 15 on this, and 14 plus 15 plus 15. This is more than 43. This comes out to be 44. So this is the answer. In this case, we have a CH3 2. So if I draw the structure, we have CH3 CH, and we have 2 CH3 on either side. If I break the bond over here, we get 15 plus 13 plus 15. This adds up to be 43. So this is not C. And in option D, we have a CH3 CH2 CH2 here, which has a peak at 43. So B is our answer. Now on to question 16. We have to refer to the data booklet and find which compounds have a peak at 3415 and 2250. If we look at the infrared spectrum, this peak over here at 2250 is for a triple bond. This peak at 3415 is for an OH or NH bond. Options B and D do not have a triple bond. These two have a triple bond, so it could be either of them. Now if I look over here, it must have an OH or an NH bond. This option C does not have it, while option A has an NH bond, so A is the answer. Now on to question 17. In question 17, we are asked why the distribution of energy start at the origin. So basically, why does the number of particles for E equals to 0 is at 0 and not over here? So why is the y-intercept at 0 instead of being at some values like this? This is because all molecules have some energy in some way. So there are no zero energy particles. So B is the answer. all molecules must have some energy, or else the graph would start from here if some molecules had zero energy. So if there were 10 molecules with zero energy, this would be how the graph started. Now in part B, we are asked that some of the gas is removed and the container is resealed and the gas is cooled. We have to find which of this option shows the new distribution of molecular energies compared to the original sample. Here, the number of moles are changing. The number of moles are being decreased. So the area under the graph, represents the total number of particles. So which in this case will decrease. So option B or D is the answer. A and C are out. Now we are also told that the gas is cooled. So if the gas is cooled, the energy will decrease. So the peak will shift to the left. So something like this. The total area will be less than before and the peak will be shifted to the left. So something like this or like this. So B is the answer. Now on to section B. We are told in question 18 that calcium hypochlorite is used for water treatment and we are given the reaction. In the first question, we have to state the type of reaction in the production of CaClO2. Now if you look over here, and for chlorine, the chlorine is being converted to ClO2, the hypochlorite over here, and CaCl2, calcium chloride over here. Over here, the oxidation number of chlorine is +1. So if I calculate it, calcium has 2, chlorines 1 is what we want to find, and oxygens is -2. We have x minus 2 times 2 for this. This is equal to 0. So x minus 2 is equal to -1. X is equal to +2 minus 1, which is +1. So the oxidation number of chlorine over in CaClO2 is +1, and over here it's a chloride, it's -1. So first, beforehand it was 0. Now it's becoming +1 and -1. So chlorine is being oxidized and reduced simultaneously. So this is a disproportionation reaction. And we have to write down the changes. So Cl2 being changed to from 0 to +1 in CaClO2, and Cl2 being changed from 0 to -1 in CaCl2. This is how we structure our answer for this question. Now moving to part B, we have to calculate the percentage atom economy by mass for the production of CaClO2. For that, we have to find the molar mass of CaClO2. This would be 40.1 for calcium, and then for chlorine it's 35.5, and for oxygen it's 16, and we multiply it with 2. We get 143.1 gram per mole. This is the total MR of calcium chloride. The other products of this reaction are calcium chloride and water, and we have 2 moles of water, so we have to multiply the molar mass of water by 2. So if I want to find the percentage atom economy, our wanted product is calcium hypochlorite, which is 143.1. The denominator will be the total product, so 143.1 for this, and then for calcium chloride, so CaCl2, the molar mass is 40.1 plus 35.5 times 2, which is 111.1 gram per mole. So this is 101.1. For water, we have 2 moles of it, so 2 into 18. The percentage economy comes out to be 49.3%. Now in part C, we are given the dimensions of a swimming pool, and we are told that the water in the swimming pool has calcium hypochlorite at a concentration of 4.2 milligram per dm cube. We have to find the mass of CaClO2 in kilograms. Firstly, we need the volume of the swimming pool. This would be 50 times 25 times 2.0 meter cube, which is 2500 meter cube. The concentration is given in milligram per dm cube, so I'll convert this into decimeter cube. So this will be 2500 into 10 cubic decimeters. Now I have the volume and the concentration, so I can find the mass from it. This would be 2500 into 10 cube dm cube multiplied by 4.2. This is milligrams. I want this in kilograms, so we have to multiply 10 to the power minus 6 over here. So this would be 10.5 kg. Now we have to find the volume of chlorine at room temperature and pressure needed to make the mass calculated over here. Firstly, we need the moles of calcium hypochlorite used. So 10.5, we have to convert this into grams, so multiply 10 cube with it, and we have to divide the molar mass, so 143.1. so gram divided by gram per mole, we get a value in moles. This will be 73.3753. We can work with 73.38 moles. Now since I have the mass of calcium hypochlorite, so I have the mass of calcium hypochlorite. From there we can use the molar ratio. So for each mole of calcium hypochlorite, I need 2 moles of chlorine, so we have to multiply that value with 2 to get the moles of chlorine. So moles of chlorine will be twice of 73.38. This would be 146.75 moles. From here I can find the volume. The molar gas constant is 24 dm cube per mole. So if I want to find the volume, I multiply 24 dm cube per mole with the number of moles 146.75. The moles will cancel out. I'll get a value of 3522 dm cube. Now moving to question 19, we have to draw the skeletal formula of 3 tertiary alcohols with the formula C6H14O. So I'll start with the central carbon. This is not the skeletal formula, I'm working out for it. I'll have 3 different alkyl groups connected to it and an OH over here. The alkyl groups combined must have 5 carbons, and the 6th carbon is over here. So I can put 2 over here. 1, 2, 3, 4. I can put 1 over here. So CH3, C2H5, C2H5. The skeletal formula would be like this. We have a CH2 on this side, a CH2 on this side. So if I match them together, this is the central carbon. I have an OH attached to it, a CH3, a CH2, C2H5 over here, so CH2CH3, and another CH2CH3 over here, which will go like this. Again, another one will be like this. Now instead of taking 2, 2, 1, the other 5 carbons, I can take 3, 1, 1. So C3H7, CH3, and another CH3. To draw this, I'll have a carbon over here, an OH over here, a 3 carbon chain over here, so 1, 2, 3, a methyl group on the other ones. Now for the other one, we can have some branching in this C3H7. Over here I had the C3H7 as CH2, CH2, CH3. Instead of that, we can have a side chain over here. So the rest is the same. CH3, CH3, OH. This is the same. And in part of the CH3, C3H7, I can have CH2, and then I can have a CH over here. I can have a CH3 on this side and another CH3 on this side. The skeletal formula will have a carbon in over here, an OH over here, a CH3 over here, another CH3 over here, a CH over here, and 2 different methyl groups CH3 over there. Now we are given that C6H14, 2 primary alcohols of this formula, A and B. They are given over here. We have to find the IUPAC name for alcohol A. So if I look over here, so 1, 2, I'm finding the number of carbons in the longest chain. So this is 1, 2, 3, 4. So this is a butanol. I'll put the OH in the first carbon. So I'll start counting from here. So 1, 2, 3, 4. Since alcohol is a higher priority group than this methyl groups. Now we have 2 methyl groups on carbon number 3. So this will be 3, 3 dimethyl butanol. Now in part 2, we have to explain why alcohol B has a higher boiling temperature than alcohol A. If you see the difference, the formula are the same. The difference is that alcohol B is more of a straight chain than alcohol A, which has a lot more branches. If something is straight chain, the London forces between them will be stronger, so there is a greater intermolecular forces between them. This is due to the fact that straight chains can have a greater area of contact when they are close to each other. If you look over here, there is significant area of contact between 2 molecules of alcohol B. If I draw another molecule of alcohol A over here, the area of contact is much less. So the London forces for alcohol B will be greater, and that causes the London forces are stronger since there is a greater surface area. This causes the boiling temperature to be higher as more energy is required to break those bonds. And that's why alcohol B has a higher boiling temperature than alcohol A. Now in part C, we have to explain why alcohol B is completely soluble in ethanol but only slightly soluble in water. Alcohol B over here will dissolve in ethanol through London forces, and it will dissolve in water through hydrogen bonds. So alcohol B will dissolve. We'll write that down, that the solubility with ethanol is due to the London forces, and the solubility in water is due to hydrogen bonds. Now usually we have learned that hydrogen bonds are generally stronger than London forces, but if we look over here, this is a very long carbon chain. This is a very big molecule, C6H14. This is a 6 carbon chain. So the London forces over here will be very strong in comparison to the hydrogen bonds. In general, as if I keep increasing the length, the London forces will become more dominating than the hydrogen bond. So the London forces between alcohol B and ethanol is stronger than the H bonds between B and water. Now in part C, we are given this organic product. This is an alcohol. An alcohol is being heated under reflux with potassium dichromate and sulfuric acid. If this reaction occurs, a carboxylic acid is formed. So we have an O over here, an OH here. So basically an O, double bonded O comes over here. Now we are heating under reflux. This is another. Now the first reaction was a primary alcohol. A primary alcohol is being oxidized into a carboxylic acid. In reaction 2, we have a secondary alcohol. We have the same reaction over here. It's being heated under reflux in potassium dichromate and sulfuric acid. And since this is a secondary alcohol, this will form a ketone over here. This is the structure of the ketone. Now in reaction 3, we have another alcohol. This is reacting with red phosphorus and iodine and then heated under reflux. So we'll have a nucleophilic substitution. You don't have to know the mechanism. So over here the OH is being replaced by I. So the same molecule, just instead of OH we'll have an I. Now on to question 20. In this question we are forming this compound propylamine from ethene. So we are given some steps on how we do it. We have to first find what reagent is used in step X. In step X, we go from an alkene to an halogenoalkane or a chloralkane. To do this, we have to react it with hydrogen chloride gas. So HCl gas. We cannot write aqueous since it's only applicable for gaseous. If it was with HCl aqueous, other products might have formed. This product would have also formed in that reaction, so it can be allowed to write that, but this is the correct answer. Now in next question we have to find the organic compound W's structure. So this is the reaction of CH3CH2Cl with KCN. The Cl will be replaced by the nitrile group CN. This will become a nitrile. So we'll have CH3 CH2CN. Now in part C we have to find the possible dot and cross diagram for N3-. I'll use a cross to represent the electrons of the first nitrogen, a circle for the second, and a field circle for the third. We have one extra electron than we usually have. Normally we have 5 electrons in nitrogen's outer shell. The fifth cross over here. We can have double bonds over here. The other 3 will be from this nitrogen. So 1, 2, 3. So we have used 3 of its electrons over here, so the other 2 will be here. We can form another double bond here. This is another double bond. We have used 2 of this full electrons. We'll have 3 left. One of them will be a pair over here, and there will be another left. Now we can bring in the extra electron. I'll represent the extra electron as a dot with a circle with a dot in the middle. This will be over here. This is from outside, another atom's electron. Maybe a sodium atom giving one of its electrons over here to become Na+. Now in part C2 we have to complete the mechanism for step Y. Step Y is when we go from CH3CH2 CH2Br to CH3CH2 CH2N3. So instead of bromine we are having N3 over here. Over here the carbon is electropositive, the bromine is electronegative. So this bond might break heterolytically. There is a lone pair of electron on N3 minus. This will attack the electropositive carbon. From here we'll get CH3CH2 CH and N3, and we'll have a bromide ion being formed as well. Now for 20D1 we are told that step Z is carried out by reacting ammonia with 1 bromopropane. We have to give the condition for this reaction. So step Z over here is the production of an amine from a bromoalkane. This reaction's condition would be to carry it in ethanolic medium under high pressure. The pressure should be above 100 kP or 1 atmosphere. And we have to suggest why the yield is low in step Z. If we look at the product over here, this is a primary amine. However, if the reaction goes on, so we can step Z can repeat over again with the primary amine, forming secondary amines, tertiary amines, and ammonium salt. So secondary or tertiary amine may form. Now in question 21, the 6 marker, we have to discuss the thermal stability of anhydrous nitrates of group 1 and group 2 elements. We are told that we have to explain the trend in thermal stability of group 2 nitrates and the difference in the product of thermal decomposition of group 1 nitrates. And we have to give equations for the thermal decompositions of sodium nitrate and magnesium nitrate. Now we have to explain the trend in thermal stability of group 2 nitrates at first. As we go down group 2, the thermal stability will increase. This would be because the size of the ions increase down the group. If that happens, the polarizing power of the cations would decrease, since the charge density of the cations are increasing over here. So the nitrogen or the NO2, so the bond between the N and O is stronger, since this is less distorted if it's less polarized. Now we have to describe the difference in product of thermal decomposition of group 1 nitrates. This difference is with lithium. Lithium is an exception. So lithium, for instance, breaks down, so lithium nitrate, this will break down into lithium oxide and NO2, while other group 1 metals will simply break down into NO2. So sodium nitrate, for example, will break down into Na, NO2 and O2. Now we have to balance this. This is a half. So this is the difference. Basically, lithium nitrate breaks down like group 2 nitrates usually do, or it forms a metal nitride. So this is the difference. And now we have to give the equations for the decomposition of sodium nitrate and magnesium nitrate. For sodium nitrate, it will break down into NaNO2 and O2. To balance this equation, I have to put a half over here. And now for magnesium, this will be MgNO3 2. This will break down into MgO, NO2 and O2. To balance this, I'll put a half over here and a 2 over here. So this is our answer to question number 6. Now we have to move to section C. Now in this question, we are given two reactions which involve the production of hydrogen. Now we have to give the reason why excess steam is used in the first reaction. If excess steam is used over here, the equilibrium will shift to the right. This will cause the production of hydrogen to increase. So this basically shifts the equilibrium to the right. That's all they need to know. The equilibrium is shifted to the right over here. Now we have to predict if T1 or T2 is the higher temperature. Over here, if we observe this, we see that the first reaction over here is endothermic while the second is exothermic. Endothermic reactions are favored when the temperatures are higher, so T1 should be higher over here. Now in part 3, we have to find the overall equation for the production in stage 1. If I add both of them together, I'll get rid of the carbon monoxide over here. So I'll just have to write the sum of these two equations. This will be CH4 plus 2H2O, and I'll get 4 moles of H2 and 1 mole of CO2 over here. Now moving on to part B, we have the third reaction in stage 1, and this involves removing the carbon dioxide using aqueous N-methyl diethanolamine. This is the reaction over here. We have to suggest one reason why the CO2 is being removed over here. This would be possibly to reduce greenhouse gas emission. If we look at this reaction, we see that a salt is being produced. This is a salt of N-methyl diethanolamine and carbon dioxide. So this will be a carbonate salt. This is an acid-base reaction, so this will be a neutralization reaction. Now we have to draw the displayed formula of N-methyl diethanolamine. So we have a CH3 over here, then we have a nitrogen, and this is joined to two other CH2OH. So a CH2 and an OH over here, and the same thing repeats over here. So another CH2OH. This is the displayed formula. Now moving into part C, we are told that in stage 2, the hydrogen from stage 1 reacts with nitrogen to produce ammonia. We are given the conditions of the reaction, where the conditions are a temperature of 700 Kelvin, a pressure between 100 and 200 atm, and an iron catalyst. We have to give one advantage and one disadvantage of using such a high pressure. If we look at the equilibrium, we have 4 moles of gases on the left and 2 on the right. So if we use a high pressure, the equilibrium will be shifted to the right, so that's an advantage. And the disadvantage of using such a high pressure would be that it requires a lot of energy and it costs a lot due to using that much energy. We'll need a lot of energy to pressurize the gases. Such a high pressure is also very difficult to maintain and it's very dangerous if it's not done with special equipments. The special equipments will cost again, so this is a very expensive procedure, so that's the disadvantage over here. When we write the disadvantage that it's expensive, we have to mention why it's like that. Now moving on to part D, we are given a graph over here. We are told that the reaction in stage 2 has an activation energy of 70 kilojoule per mole, and the uncatalyzed reaction has an activation energy of 290 kilojoule per mole. We have to complete the profile for the catalyzed and uncatalyzed reactions. We have to label the activation energies and the enthalpy change del H. The del H will basically just be this part over here. This is the change in enthalpy. From previous data, we know that this value over here is minus 92 kilojoule per mole. Now if we look in this portion over here, we have 5, 10, 15, 16, 17, 18 and a half boxes, which represents 92 units. So each of these boxes are 5 units each. So we have one unit being 92 by 18.5. So each small box over here represents this many units in kilojoule per mole. We'll work with 5 over here. This will be 92 into 5 by 18.5. This value over here is around 25, so 24.9. We can work by considering this to be 25. Now the first activation energy is 70 kilojoule per mole. This is for the uncatalyzed reaction. So we can find the number of half box. So number of this size box it will cover. This will be 70 divided by 24.9. So this is 2.8. 1, 2, and this is 2.8. So that will be the peak of the uncatalyzed reaction. The activation energy in this case would be this over here. So from the level of this reaction up to the peak, this is the activation energy when it's catalyzed. We are told that this is E cat. Now when it's uncatalyzed, it's 290 kilojoule per mole. So we have to find the number of boxes again like this. This will come out to be 11.7. So if I go over here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then we go 0.7. So this is 0.246, somewhere along here, somewhere along this. So this is for the uncatalyzed reaction. For this reaction, the activation energy would be from here, this. Now we have to suggest why the use of catalyst makes the stage 2 more sustainable. If the activation and since the catalyst is used, the activation energy is almost 1/3. So we'll need much less energy and much less fuel to carry out stage 2's reaction in this case when it's catalyzed, which makes it more sustainable since we don't have to burn as much fuel. So less fuel is needed over here. Now for part E, we are given that in stage 3 nitrogen monoxide produced in the reaction between NH3 and O2. The conditions are given that it needs a temperature of 1100 Kelvin with a platinum rhodium catalyst. This is the reaction over here. It has an enthalpy change which is exothermic, and we have to answer why a high temperature is needed. We cannot talk about the equilibrium over here since a higher temperature will shift the equilibrium to the left, which would actually be a disadvantage. We have to give a reason why this is needed. A high temperature is if a case of exothermic reaction is given and we are told that high temperature is needed, it's always going to be about rate. So at low temperatures, the collisions between particles are not do not have sufficient energy to be successful. So we have to increase the temperature so that the rate increases. So the main reason why a high temperature here is needed is to raise the rate. Now we have in part 2 we have to suggest why only a small amount of energy is used to maintain such a high temperature. This is because the reaction over here is exothermic, so it releases energy. So if this reaction keeps on occurring, this is an exothermic reaction. If this reaction occurs, it will let out a lot of thermal energy, and that thermal energy is again used to maintain this high temperature. So the forward reaction being highly exothermic is the reason behind us not needing to use a lot of energy externally to maintain this high temperature. Now in part F, we are told that the nitrogen monoxide from the first reaction in stage 3 is cooled and converted to nitrogen dioxide by reacting that with more oxygen. So this is the reaction over here. And from that, nitric acid is produced by adding water to nitrogen dioxide. We have to explain how adding water in the second reaction affects the yield of NO2. In this case, if water is added in the second reaction, we'll have more nitrogen monoxide being produced and we'll have less NO2. So if I go to this equation over here, now we have less NO2 and more nitrogen monoxide. Since we have more nitrogen monoxide and less nitrogen dioxide, the equilibrium of this reaction will shift from the left to the right. So more NO2 is being produced again. This will increase the yield of NO2. The NO2 is removed over here in the second reaction. This will cause the equilibrium of the first reaction to shift to the right, increasing the yield of NO2. This is how we structure our answer. So this is how we'll write down our answers. Now for part G, we have a Hess cycle over here and we have to complete it. Now from the data we have to find out the enthalpy change from NH4NO3 solid to aqueous. So this is the change over here, NH4NO3 solid being turned into NH4NO3 aqueous. So this will be plus 25.6. If we look at this reaction, so this arrow, NH4NO3 solid being produced from its base elements in their standard forms. This value over here will be the change in standard enthalpy change of formation for NH4NO3, which is minus 365.6. So this will be minus 365.6. Now we are given values over here, but we do not know what's in the middle. If I go over here, I can see that the minus 32.6 joule is over here. So before this step, I must have had NH3, so HNO3 liquid. And I must have also had NH3 gas from beforehand, because if I didn't have it over here, I wouldn't have it over here, since nothing else is reacting except this HNO3 liquid turning into HNO3 aqueous. Now from here we have to find the enthalpy change for the reaction between NH3 and HNO. So this reaction over here, if I look at the reactions that are clockwise, this is clockwise, this is clockwise, this is clockwise, the other two are anti-clockwise. So we'll add the three reds up, and this will be equal to the two blue ones. So the red ones are the reaction enthalpy, or the enthalpy change of reaction. Then we have minus 32.6, minus 220.2, and on the other side we have minus 365.6 and plus 25.6. We'll move all the other values to the right, and we'll get a value for del H, which will be minus 87.2 kilojoule per mole. If I want to show the calculation, this would be the enthalpy change being minus 365.6 plus 25.6 plus 32.6 plus 220.2. Now for part H, the last question, we have to suggest two reasons why it's more profitable to carry out all four stages at the same site instead of using different sites. We can think of a lot of different advantages of doing it in the same site. I don't have to pay for transportation, I don't have to transport stuff from one site to the other. I'll not have to use as much land. I can do my production in a smaller land. It's also cheaper to produce all the other stuff than just buying it from other people. This goes more vague. We can also talk about how we can use the energy that we get from the exothermic reactions to power up other reactions. And we'll also be able to save time, since there won't be a bureaucratic mess about handling the shipments of the products. So I don't have to, for example, if I look at this reactions, I don't have to transport hydrogen in different gas tankers to another site. This would be a very big mess to organize, and I'll need to hire more people if I have to do this. So if I do it in the same place, I can also use a smaller workforce to get the same results. So we can write any two of those points. The most obvious points to me would be the transportation cost. This would be this is the most clear point over here, that we don't have to spend on transportation. The second point that would come to my mind would be about land, since less land would be required if we're doing it in the same site than spreading it out over a few different locations. And that's it for this paper.